Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am very happy to have Jorge Morales with us today. Hi, Jorge.
Hello. Thanks for the invitation,
Well,
Frank.
we're agreeing to talk about your very lovely article, which we'll get to here in a little bit. And Jorge, what's your geolocation? Where are you located at?
So currently I'm in Bedford, Massachusetts, in the East Coast.
Okay, very cool. Let's see. It is February 10th of 2024 as we record this. And is Massachusetts getting its spring, or are we still sort of in the winter mode?
No, we are purely in the winter, so during this weekend we had like 8 to 12 inches of lovely snow and you know, clean the car. The
Clean the streets.
roads are hard to drive.
Well, let's see. I'm in Phoenix, Arizona, and we definitely did not get 8 inches of snow this weekend. But we are definitely in our spring mode. We are definitely warming up. So we'll get up into the mid 80s Fahrenheit today or something like that. So
Oh wow, 80.
it'll be toasty.
That's good.
Yeah, it's very nice. It'll melt that snow in Massachusetts, no problem. So, and Jorge, let's see. What do you like to do for research?
So for research, I'm very interested in neutron stars. I am very interested in gravitational wave searches. So in summary, modeling and simulations of neutron stars and data analysis of gravitational wave data.
Very cool. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era. People go grab a copy for free. Limiting rotation rate of neutron stars from crust breaking and gravitational waves. And Jorge, take us away.
Thank you very much again, Frank, for giving me the opportunity to discuss this article. Um, so this was essentially my last article from my PhD. Previous to that, I did two articles exploring a slightly different but somehow related topic. So I studied anisotropies, material anisotropies in neutron stars.
Okay.
And for that, it was very, very important to develop a new way to solve the differential equations of neutron star stellar structure
Okay.
to capture asymmetric deformations and things that could give rise to gravitational waves.
Right.
So when me and my advisor were talking about that, we went into this very interesting question, which is how fast should we spin up a neutron star from rest so that the neutron star crust breaks?
Okay.
And if it breaks
Hmm.
asymmetrically, which is an assumption we have in this paper,
Okay.
what are some gravitational wave implications? And that led us to use the finite element method formalism
Cool.
to write up some cool equations. And what we found was extremely interesting, as I would say, as I will say some
We'll say so.
in some moments.
Very good. Okay.
Yeah, so neutron stars are these very dense and compact objects. They are divided in two main layers. You have the fluid core, and you have the outermost kilometer, which is the solid crust.
Hmm.
And of course, we can do uh, more sublayers of that, as you probably know. But those are the two main things of an neutron star, and of course, an ocean. But
Right.
I particularly care about the fluid core and about the solid crust.
We want to crack that.
So yeah, so now that we have entered into the gravitational wave era, that's how
Woohoo.
astrophysicists call it. We're very interested in mass deformations and how these mass deformations could couple to the rotation of neutron stars to emit detectable gravitational waves.
Okay.
So there are some accreting neutron stars that people have studied through the years. One of them is Scorpius X1.
Hmm?
There it is.
There you go.
So people have done continuous gravitational wave searches trying to detect the first continuous gravitational wave
Right.
for this system. But unfortunately, the parameter space that we need to search on is extremely large, and the sensitivity is limited
Yes.
by the amount of computing power we need to carry on these searches.
Fair enough.
So, therefore, although we have been able to put some upper limits on the deformation that would emit detectable continuous gravitational waves, or in this case, not so detectable, right?
Yeah.
Uh,
Okay.
People have not been able to reach yet the interesting ellipticity upper limits.
Fair.
Okay.
Mm-hmm. Mm-hmm.
So why I mention Scorpius X1, because this is an example of an accreting system, and that's to zeroth order, as to say, what we are going to try, or what we tried to model in this paper, in this letter. So in this letter, as I was saying, we did some finite element simulations of the neutron star crust to see where it breaks first and when it breaks.
Right.
And we can go perhaps to the formalism to
Yeah.
describe some of the equations.
We're going to do a finite elements here on a Newtonian star with a polytropic EOS. And here we go.
Yep. So equations 1 through 3, I think most of the people will know what those equations are. The
Mm-hmm.
Euler equations of stellar structure, the Newtonian version, of course. We use those equations to obtain things such as the gravitational potential, the density as a function of radius, and gravitational force, so on and so forth.
Mm-hmm.
And we obtain the isotropic zeroth order structure of our neutron star that is going to be perturbed then with the centrifugal force. So perhaps
Okay.
if you go, no, you're right. Sorry, you're good there.
Okay.
Um, so we use Newtonian physics, as I said. We use a polytrope equation of state, which has been good to model neutron stars
Mm-hmm.
times. Um, we assume that the crust has a shear modulus, well, a good angled average shear modulus that models relatively well all of the crust. And we go on and we solve the equations 1 to 3, obtain the structure.
Okay.
And then what we do is that, and this is a particular thing we did in this letter, we obtain so we assume that the neutron star is spinning up from rest. This is very important. The neutron star is spinning up from rest
Okay.
roughly as the neutron star that starts to accrete do.
Okay. I'm with you.
Right?
Mhm.
Okay. We first assume that the neutron star is all fluid.
Okay.
Why we do that? Because we want to obtain the perturbations to the gravitational potential
Uh-huh.
when the centrifugal force starts to act on all of the star.
Okay.
And then we can use that perturbed gravitational potentials in equation 8 that you have in the right panel
Yes.
of the paper. Why we do that? Because of two reasons. So first of all, the neutron star crust has roughly 1% of the mass of the neutron star.
Yes.
So we don't expect that assuming that the crust is solid will change much the perturbed gravitational potential. And of course, that leads us to our second point of why we decide to do that.
Okay.
And it is because it helps us to save uh, some computing power because to obtain the perturbed gravitational potential using finite element method will involve significant
Yep.
time and significant computational resources.
Yes.
So the problem is already intensive computationally. I mean, if we start trying to solve for the perturbed gravitational potential, it will take probably forever
Quite a
to
while.
to
Hmm.
get it.
Yes.
So
Get it.
once we obtain the perturbed gravitational potential, we go on and solve equation 8 subject to the boundary conditions of the continuity of the traction between the solid crust and the fluid core,
Okay.
and outside where there is the transition from crust to ocean of the neutron star.
Um, with you. Hmm. Okay.
Okay.
Yes. Okay. Gotcha. Hmm.
So perhaps now we can go to the next page.
Okay. There. Do, 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 do.
For equations 4 and 5 actually are the equations where Fi is the centrifugal force, which we
Mhm.
treat as a perturbation to the background star that we obtain with the earlier equations. Of course, 5 is the perturbed version of the Poisson equation for gravity.
Uh-huh.
And as I said, equation 8 is the one we use uh, to use finite element simulations to solve for perturbations in the neutron star crust and obtain our results.
I'm with you. Good.
Okay.
Okay. Let's slide on down maybe to where you want to go next.
Yeah. So perhaps to figure, is there's a figure in the page above?
Yeah. Figure one. Hmm.
Yep.
Okay. Let's
There
take.
it goes. Okay. So, yep. Okay.
Hmm.
So those are the different components of the displacement from the elements of the
Okay.
solid crust as a function of the polar angle.
Yes.
Okay?
Yes.
So one of the conclusions that we reached in this letter is that the crust breaks at about half of the Kepler frequency,
Okay.
and it does so near the equator
Hmm.
and near the most bottom part of the crust.
Like
Um,
deep in, deeper in.
yep.
Yeah. Okay. Hmm.
So why is that? Well, here you can see a snapshot of it. You know, the radial displacement, which is
Hmm.
that line that you're
Yes.
showing,
Hmm.
is highest at about pi over 2, which is the equator of the
Yes.
neutron star.
Yes.
Okay.
Hmm.
And then you have the other two lines, if you'd like.
Data components. Yeah. Curves. Hmm.
R1 is the bottom of the crust, R2 is the top of the crust,
Ah. Yes.
and
Okay.
U theta is slightly larger in the bottom than in the crust. And that is what gives us one of the most important results that the neutron star crust
Got it.
breaks first near the bottom,
Yeah.
near the equator.
Mm.
Near the equator, this result was obtained a few years ago,
Okay.
but people modeled neutron stars as a constant density star.
Mm.
And this is one of the things we found, which was very interesting, is that when we put this polytrope model, which is obviously non-constant
Not
density model,
constant, right?
um, you have that the cross break at the bottom. And this is extremely interesting. Why? Because remember that I said that we postulate that when the neutron star cross breaks
Yes.
after spinning up a certain amount, it does so non-axis symmetrically. Okay?
Yes.
And previous studies have shown that the region near the bottom of the crust is what is going to contribute most to the deformations that will produce continuous gravitational waves.
There you go. Cool. I'm with you.
Okay?
Mhm. Yep.
So this is a very, very important result that is illustrated in this figure. So perhaps if we go,
Very nice. Okay.
yep, we go maybe to the next figure,
Figure two.
figure
Okay.
two.
Strains. Mm-hmm.
Okay. So there you have there you have somehow the same thing, explained in a different way. Von Mises strain
Mm-hmm.
uh, is an effective strain that we calculate in the crust.
Yes.
The breaking strain of the neutron star crust has been calculated to be about zero point 0.1, about zero point 0.1, with some uncertainty, of course, as we mentioned in the letter. Could be,
Mm-hmm.
for example, 0.05, could be zero point 0.8, zero point 0.1. There is some uncertainty there.
Okay.
And uh, the same happens through all of the crust, including the region near the base, where you can expect to have these weird forms of dense matter, which has been called nuclear pasta.
Oh yeah, sure. Mm-hmm.
Okay.
Mm-hmm. Yes.
So what you see here is again the same kind of thing, right? That the breaking strain is reached first in the black line,
Yes.
near the bottom, near the top. And if you would be able to fill out this space between the two lines, you will see just, black dots corresponding to the different elements,
Ah.
um, to different finite elements,
Yeah.
filling out the space between these two curves. Okay.
Okay. Okay.
We did not show them because we thought this kind
Mm.
of visualization is a little more clear.
Yeah, it's clear this way. But yes, I get the point. It would be filled in. Yes. Uh-huh.
And another important point, and this is why we included this plot in addition to the first one we showed,
Mhm.
is that when the cross breaks near the bottom, most of the crust is significantly strained. It's not like the bottom breaks and all of the
The rest
other
just sits there.
regions of the cross is sitting there on the
Yeah.
floor. Yeah, so it that doesn't happen. Most of the crust is very, very strained, and we can say about to break as well, giving perhaps more contributions to the deformation, which would then produce gravitational waves.
Yeah. So it's the whole crust, not just the bottom part. Right?
But the bottom breaks first,
Yes.
and
Oh
that
yeah,
is
yeah.
extremely
Mhm.
interesting. That is
Propagate.
extremely interesting. Um,
Oh, that
so
happens.
that's
Cool.
what that plot is narrating.
Cool. Very good. Okay.
One question that people might ask is, and perhaps we can go to figure three.
Yeah.
Figure
Got
three.
versus
Yep.
rotation frequency. Okay.
Yep.
All right. Bang.
So one of the questions people might ask is, well, what happens if we change the mass of the neutron stars? Because we know that neutron stars are extremely diverse, and there are some that have higher masses, some that have smaller masses. What would happen if you change the mass? And of course, you have then uncertainties in the equation of state of and all of that, right?
Oh, sure.
So what would happen? Well, this curve shows the result for 1.4 solar masses star,
Mm-hmm.
2.0 solar masses star,
Uh-huh.
and qualitatively you get the same.
Yeah, pretty
The
much.
neutron star breaks at about half of the breakup rate for both kind of stars, the
Okay.
less massive one, the more massive ones. And now that I mention it, this is extremely interesting because coincidentally, the fastest neutron star is spinning at about half of the Kepler
Oh,
frequency,
breakup. Yeah. Mm-hmm.
the
Okay.
breakup frequency, right?
Yeah.
The rotation rate at which the star starts to shed mass, right?
Hmm.
So this result is very interesting because it suggests then
Cool.
that the neutron star uh, limiting frequency might be related to the strength of the neutron star crust.
Okay, very good. And that has been a question for quite a while, right?
Oh yeah,
What
yeah,
is the maximum spin? Yep. Mm-hmm.
yep.
Mm-hmm.
And it's interesting because we know theoretically that neutron star could be spinning much faster than that. So why
Why
we
not?
haven't observed a neutron star spinning near the Kepler frequency?
Mm-hmm.
Well, it might be because of this, because the
Prospect.
crust is strained by the centrifugal force.
Oh,
The crust, uh, that causes the crust to break when the star reaches about half of the Kepler frequency.
yes.
And the neutron star starts to radiate
Eight.
away energy in the form of gravitational waves. And that's why, although it keeps accreting, it doesn't speed up further than that because you have this, what people call torque balance.
Uh-huh.
You
Yes.
gain torque from accretion, you radiate out torque in the form of gravitational waves.
Mm-hmm.
Okay?
It's got like
And
its own
this
radius
is
now.
this is, I would say, one of the most interesting results.
Indeed.
I'm not saying that this is the mechanism which, right, which limits the rotation of neutron stars,
Uh-huh.
but what I'm saying certainly is that it is a possibility
Absolutely.
and, a reasonable possibility,
Mm-hmm.
more
Said
than
like
that.
a true theorist. There we go.
Yep.
Very good. Very
Okay.
good. Oh, and we have a
The table.
yeah.
Yep.
Okay.
So,
Radius.
yep.
Okay.
This is a very interesting table. So, we was it figure two? Could you go back to figure? No, it's figure three.
Figure three. So they're right next to one another. So
Yeah,
let's
yeah. What we
zoom
were
out a little
seeing
bit so we
was,
get them both.
yeah, yeah, yeah.
So we'll get
So
both.
there we said, okay, what happens if we vary the mass and
Mm-hmm.
let the radius be the same? Okay. Now the question arises, what happens if we change the radius then?
Yep.
So for a 1.4 solar masses neutron star, we try to answer that question using this table. But there
Mm-hmm.
is much more in that table because
Mm-hmm.
what we try to show in that table is not only the effect of the uncertainty in radius, but also the relativistic effect, right? So in a real neutron star, you will not need only Newtonian physics, but also, and actually, you will need general relativity to model the neutron star with super high fidelity, right?
Okay. Mm-hmm.
So what this table tries to show is that the effect of general relativity is not expected to change much the results that we obtain in this
Okay.
letter,
Okay.
right?
Okay.
So,
Okay.
first column is the varying radius
Right.
of the neutron star, of the 1.4 solar masses neutron star.
Mm-hmm.
The second column is the Newtonian Kepler frequency.
Yes.
Third column is the relativistic Kepler frequency. And if you look at the numbers, it's about one third less than the Newtonian Kepler frequency,
Yeah.
right?
Uh-huh. Yeah. Mm-hmm.
Um, Delta R E over R, that's the change in the radius, fractional change in the equatorial radius
It's the E. Mm-hmm.
for a neutron star that is strained 5% and 10% of the total radius. And this is a star that is relativistic. And this was obtained not by us, but by the reference in the note. Okay.
Uh-huh.
And on the right-hand column,
Thank
you
you.
get the frequency at which you reach
Max
the
strain.
maximum strain.
Yeah.
Remember that I showed you that there is an uncertainty in the strain, in the breaking strain of the neutron star. Could be, 5% of the radius, could be 10%.
Right.
Um, but the numbers you see there are the frequencies that we estimate that are needed to break the crust of the
Cool.
star.
Yep. Yep. I'm with
And
you.
we did so using some of the numbers from the fourth column, the
Okay.
column that's previous to that one.
Mm-hmm.
So we don't expect general relativity to change our results by much.
Right. Okay. Good. Good. I'm with you. Okay.
So
Very.
one of the results that I forgot to mention, and I'm sorry that I'm going back to a previous figure,
It's all good. It's all good.
is that when you put the star spin up, um, regions near the pole sink, okay? Because the centrifugal force there is
Oh,
zero, so
yeah,
you
yeah.
only have gravity there, right?
Okay. Yes, yes.
And the equator bulges out, okay?
Correct. Yes. Then fat.
And that is something that was interesting, not necessarily a very important result, but something that is interesting and help you to get the full picture of what's going on.
Yes.
Yeah, so perhaps you could go down now.
Okay. Sure. Let's see. We have the discussion. You want to go discussion? Want to go farther up?
Yeah, sure. I've mentioned most of it, but we can go there. So that section that you're highlighting just explains how we got the numbers from the tables. Equation 12 is the fractional differences in the moments of inertia or the ellipticity, as
Uh-huh.
people in the gravitational wave community calls it.
Yes.
I'm going to discuss a bit about the equation 13 because it is very, very important.
Yes. So what's the
Okay.
tip?
So the intrinsic gravitational wave strain, which is different from the strain we've been talking about, right?
Yes.
It's
Uh-huh.
the
Yeah.
amplitude of the gravitational waves.
Yes.
Okay.
I'm with you.
So the gravitational wave strain goes as the square of the rotation frequency of the neutron star in this case,
Yes.
and is directly proportional to the ellipticity.
Uh-huh.
So the rotation rate takes, I would call it a heroic role in the strength of gravitational waves.
Okay. I like
Okay,
that analogy.
that's a hero. That's a hero right there. The ellipticity is important as well, but because the strain depends on the square of the
Yeah.
frequency,
Okay. Okay. Got
it
it.
is more important. And one thing that we got here is that the neutron star could emit gravitational waves when the cross break asymmetrically at about half of the breakup rate,
Yes.
which is about the maximum rotational frequency that have been observed in neutron stars. But
Okay.
we're talking about some interesting objects right here because, again, the gravitational wave strain goes
Mhm.
like the frequency squared, right?
Yes.
Okay.
Yes.
So we expect the gravitational wave strain of the waves emitted by this mechanism to be high. Unfortunately, as I was mentioning, the surges of gravitational waves from neutron stars that are accreting, the searches are very, very computationally expensive.
Yes.
And that, again, that limits the sensitivity. But as the searches improve, there are more techniques, the sensitivity of the detectors get better, and that
Absolutely.
will happen because we have the 3G detectors coming out in some years.
Hmm.
Uh, as those things happen, we expect that we will be able to approach the interesting ellipticities, to start to observe gravitational waves that would be emitted by these ellipticities in these systems that could go, according to our calculations, from an ellipticity of 10 to the minus 8, perhaps, or
Two.
10 to the minus 9. So that's why
Mhm.
equation uh, 13 is extremely
Yep.
important.
Yep.
Okay.
This is what you're going to be observing. Work.
But of course, again, right now, uh, the computational resources and the time, I would say, limits us, but that's expected to improve in the next few years. So, I mean, with that being said, and with the fact that the ellipticity emitted by this mechanism could be of the order of 10 to the minus 8 or 10 to the minus 9, I think that's uh, all I wanted to mention and point out, as Frank is highlighting, that the strength of the crust or crust breaking may limit the rotation rate of neutron stars, and that is very exciting from gravitational wave perspective because strain goes like the frequency squared, and there could be significant ellipticities induced because the cross breaks first, according to our simulations, near
Mhm.
the bottom, where the deformations could be larger and contribute more to the continuous gravitational wave emission.
Right. And that breaking need not happen just once, right? One could imagine it
Oh
happens.
no, no, that's just a starting point.
Yeah, exactly. Yeah.
But I mean, I showed in figure, I believe it was 2 or 3, that most of the crust is nearly to be maximally strained, right? It's significantly strained. It's
Yeah.
significantly deformed.
Okay.
So we could have
Yeah.
further breakings that either increase or decrease the electricity, but
Yes.
from our perspective, the increasing of the electricity is the interesting portion, right? So yeah, we could have, as Frank said, breaking in other parts of the crust
Here we
that
go.
could
I knew that was
contribute to
one.
louder gravitational wave signals.
Right.
Yep.
Very cool. Awesome. Beautiful work. Beautiful work.
Thank you very much.
Yeah, Jorge, I want to thank you so much for walking us through your very awesome APJ letter. Very nice.
Oh, thank you very much for inviting me. Do you have any questions that you would like to?
Sure. Let's see, you touched on it a couple of times
Uh-huh.
in various forms. So let me ask, where do you think we go from here, given the published article? You mentioned, that they're very computationally intensive, but maybe that'll be relieved in some time. Is that because we're going to start running on thousands of processors, or you're just waiting for the clock speed to get up on those processors? There's also, you mentioned a couple times, you're using a polytropic equation in state. What if we tried
Yeah.
something non-polytropic? Let's put it that way. And then observations, of course, are going to be continually improving. They'll get more sensitive to the continuous
Yep.
frequency regime. And so just what do you think are sort of the next steps that we go on determining what is the maximum rotation rate of a neutron star?
Yep. So I think you touched all of the points I wanted to mention. So
I'll let you dig in. Go, go.
I'm just going to mention how I think this could be done. So first of all, I think that, as you were saying, we should try to use perhaps more resources to,
Hmm.
do the calculation and
What's a typical runtime for one of these? Is this days,
hours.
hours, minutes, weeks?
Half an hour to about an hour with the finite element software we use.
Okay.
Okay.
On how many processors?
Um, Not so many of them, perhaps
That's
12.
that's fine. I'm just trying to get a handle. So about an hour on 12 processors, roughly.
But we did use a somehow powerful and fast computer, so it could
Mhm.
take more in a normal computer.
Okay.
So we were using a very, very fast computer optimized for scientific computing.
Uh-huh. Sure.
Um, Perhaps that's one of the ways, trying to find a way to do this calculation in a cleaner manner, obtaining the perturbed gravitational potential
Yes.
using
Yeah.
the solid crust. Although, again, I don't expect that to change much the results.
Mm-hmm.
Second thing, and you mentioned it as well from a modeling and simulation standpoint, would be what if we add realistic equations of state?
Mm-hmm.
How would that change the results? But of course, that would then lead in tandem to the inclusion of general relativity.
Yes. Right.
So, what happens when you have realistic equations of state with general relativity?
Mm-hmm. Dynamic space-time.
What the equations look like, how we might solve the equations, and
Oh,
what
okay.
differences the results have from the results we obtain in a Newtonian manner. Where does the cross break?
Mm-hmm.
At what frequency the star is spinning, right?
Mm-hmm.
In our letter, we say that we expect the frequency to be slightly smaller, but let's prove that using modeling and simulation of general relativity.
Right. You could even
Or
do a post-Newtonian as an
post-Newtonian,
intermediate step, right? You don't have to do the
of course.
full
You could
dynamic
use
space-time.
post-Newtonian.
But yeah. Mm-hmm.
Absolutely, absolutely. That's another possibility. And for people that are detecting or searching, not detecting because there is no detection yet, but for
Not
people,
yet, but they're looking.
yeah, but for people that are, oh, and another thing before I move that, before I move on from modeling and simulation, another thing would be to consider an accreted crust equation of
Oh,
state. Okay?
yeah.
Because we
Right.
don't we do not consider how the composition of the crust of the neutron star in our model changes
Changes.
when there is accretion.
Uh-huh. Uh-huh.
That is another very
Uh-huh.
important step, in my opinion.
Uh-huh.
Can we simulate what happens when the star is accreting material and the composition is changing, right?
Ooh, yes. Mhm.
That would be a very
That's
cool
a
thing
good
to
one
do.
too. Yeah.
And we mentioned actually in the letter that we expect the ellipticity maybe to decrease a little bit if there is not another mechanism,
Okay.
because I mean the accretion could sink some of the
Oh,
material
sure. Pushes down.
that is
Sure.
deformed and broken, right?
Sure. Okay.
Okay. So that is another important step in modeling and simulation. And now moving to observations, I would just encourage people who are searching for this wave to keep doing so, uh, to search for some continuous gravitational waves from systems that are accreting,
Yep.
and keep doing what you're doing. Keep improving the search techniques.
Yep.
I think that we will have a detection in 3G in 3G era, but
Ooh, there's a
that's
bold one. There's a
yeah,
bold
yeah.
prediction.
It's a bold one, and let
But
me
I'll keep
say
my fingers
something.
crossed. I'll keep my fingers crossed.
Fingers
I mean, I
crossed.
hope it does. I hope it does. I really do.
Yeah, no, and let me say something. I mean, I know people who have been doing this for over 20 years,
Yes.
and I am more optimistic than they are probably, right? But but when I say I expect a continuous wave detection in the 3G era, I expect a detection, and I would encourage people, for example, in the Max Planck Institute in Hanover, in the LIGO, Virgo Kyra collaboration in
Yes, yes.
Australia, that are looking for these gravitational waves. I would just encourage them to keep doing so, because I think uh, I think when we get to the 3G, a detection is unavoidable, I would say, but
Inevitable.
inevitable. Yeah, inevitable. And again, might be optimistic because I've only been doing this for about 5 to 6 years. But Um, I that's what I think.
Well, the optimism associated with shorter trajectories is always needed. It's always wanted, right? Because if you just listen to, on the other end, nothing's going to happen. Nothing's going to happen. So,
Right, right.
so that optimism is much needed.
But the other side of the coin is needed as well, right? Because
Fair, right? You got to
we
be
need some
realistic.
people to provide a more realistic perspective,
Yeah.
right?
Yes.
So I think both sides are
Oh, well, it probably meets in the middle somewhere, right? Where you're suitably optimistic, but
right,
a little
right.
realistic too. So, it's all good. It's all good. Jorge, I want to thank you so much for walking us through your very awesome article. That was nice. Thank you.
Oh, thanks for the time, Frank, and hope that a detection comes soon.
I do too. And everyone, I hope this made your astronomy day, your neutron strained detection day just a little bit better. And we will see you on the next one. Bye
Bye bye.
bye.